Okay. Problem 7.24 says the switch shown has been open for a long time, and before closing at time, it's been open for a long time before closing at time equals 0. Write the expression for the capacitor voltage Vt for t equal or greater than 0. All right, so at time less than 0, this is what our circuit's going to look like. Right? We already know right ahead that our capacitor is going to turn into an open circuit, right? So what we can do is we can go ahead and analyze the circuit, and we can find the voltage. I'm going to call this V2. We're going to find the voltage of V2, V1, which is the voltage across the capacitor since our ground is at the bottom. Okay. So KCL 20 milliamp equals I1 plus I2 plus I3. We know that I3, since capacitor turns into an open circuit, it's 0. And then we have equation for components, right? I'm gonna I don't know what that was. Okay, this is for our time. We're gonna use this image for later. Okay, so I1 is equal to V1 over 20K. I2 is equal to V1 over 60K. And then I3 is equal to V1 minus V2 over 10K. So we have 1, I2, I3, V1, V2. So let's go ahead and you do maxima. Plus 20% plus 1 plus I2 plus I3 equals 0. I1 equals V1 over 20,000. 2 equals V1 over 60,000. 3 equals 2 V1 minus V2 over 10,000. 1, 2, 3, 1, 2. All right. So this is what maxima gives us for at time less than 0. So now we're going to do at time greater or equals than 0. So we want to focus on V2, which is the voltage across the capacitor, right? That's what the question's asking for. Find the expression for the voltage across the capacitor. So when this switch closes, then our circuit automatically turns into this. Yeah, so you want to focus on the right side, because this current here is going to go, current is going to follow the path of least resistance. So no current, none of this current here is going to be dissipated through here. It's all going to go here. So that's why we cut this off. So yeah. All right. So then I'm gonna call this IC, I1, I2, right? All right, so do KCL, IC. Oh, forgot to label my nodes. Sorry. Oh, actually, no, I'm gonna call this. I'm gonna call this V1, V2. Okay. IC equals I2 plus I1, right? Then we want to do the EFC. You know that IC equals 40 e to negative 9 minus dV2 dt. We're going to call this S later. IC equals to V2 minus V1 over 10K. I1 is equal to V1 over 60K. I2 is equal to V1 over 20K. Right. And yeah, so I think we have 2, 3, 2, 4, 5. Yeah, so we have 5 equations. So we do this again. C equals I1 plus I2. IC equals to 40 times 9 times negative S equals to V1 minus V2 or V2 minus V1 over 10,000. V1 over 60,000. V1 over 20,000. We have I1, IC, I1, I2, V1, V2. Cool. So we get this. So these are our values, right? So it says, once again, the question is asking expression for the capacitor voltage VT. So our capacitor voltage is going to be what we're going to be looking at is V2. So V2 is equal to negative S over 1,000. We're going to turn this 1,000 here times V2 equals to negative dV2 over dt. And this is going to tell us this. So we know this. This 1,000 V2 is equal to V2 over 1 over 1,000. So this is going to be our time constant, right? Make more space, or yeah. So yeah, right. So now we want to look at our equation here. So we know that VT are so at V at time infinity, our capacitor is going to discharge, so it's going to have 0 volts. So, 0 plus our initial voltage in the capacitor is 300. 300 minus 0 e to the negative t, right? Divided by 1 over 1,000. So this is what our equation is going to look like. So yeah, the expression for our capacitor voltage at time greater than 0 is going to be this equation.